In this video, we're going to do a quick overview of how to use a periodic table to determine the number of protons, electrons, neutrons in an element. We're also going to take a look at how to draw a Bohr-Rutherford diagram. So here we have a periodic table. Your periodic table has groups or families, so they are the columns going down top to bottom. So this is a group, this is a group, this is a group, this is a group. So we have groups all the way across, and we have 1 all the way to 18. So there's 18 groups in the periodic table. And those are the vertical columns. We sometimes call them families, 18 groups or families. You'll also notice that the periodic table has rows. So this is a row going all the way across onto here. This is another row over here going all the way across down to here. So those rows, the horizontal ones, those are called periods. And so there's 7 periods in the periodic table of elements. This one over here being the 7th. These ones don't count as their own periods. They actually belong in here. So there's 7 periods in the periodic table. Okay, and that's going to be important soon. Also remember that elements can be divided into different groups or different classes or different types of elements. There's metals, nonmetals, and metalloids. You can see a little bolded staircase here that divides the periodic table into its different classes of elements. And so typically things to the left of the staircase are considered metals, and things to the right of the staircase are considered nonmetals. So that's important to remember, especially as we go into naming compounds later on. So let's say that you want to find the number of protons, electrons, neutrons in an element. We can select any element, doesn't really matter which one. The strategy is always the same. The numbers might be a bit different, but the strategy is always the same. So let's deal with fluorine. Fluorine is over here. You look at this over here, and there's a lot of numbers, but let's focus on the numbers at the top here. This number at the top, if you forget, your periodic table usually has a legend. It tells you that's your atomic number. So for fluorine, I kind of scratched it out there. For fluorine, the atomic number is 9. And so what that tells you is that for fluorine, atomic number being 9, there's 9 protons. Remember, protons are positive, so we put P+. Okay, and what usually has to happen is in a neutral atom where there's no overall charge, the electrons being negative have to be the same as the protons. So right away, we're going to put 9 electrons. So the atomic number tells us the number of protons, and it's also the number of electrons. Then, if you want to find the number of neutrons, you have to understand that atoms weigh something. Their weight does not come from electrons because they're very light. It comes from protons and neutrons. So the mass of an atom, let's call it M mass, is equal to the number of protons plus neutrons. So if you want to find the number of neutrons, you would just have to do the mass minus the protons. That's your number of neutrons. Don't get confused by these equations. It just means take this big number here and then do minus the little number up here. So 19 minus 9. So we're doing 19, which is the mass, minus 9 gives you 10. So there are 10 neutrons in fluorine. Sometimes you'll notice there is a decimal place. You can just round that. So 12.01 will round to 12, 10.81 will round to 11. So just round that up or down depending on what's more appropriate. But the point is that we use these two numbers to figure out the number of protons, electrons, neutrons, 10 neutrons, in fluorine. Ignore the other numbers for now. Those will be important later. But for now, just take a look at those two numbers. And again, your periodic table usually has a legend near the top that tells you what the different numbers refer to. So we have the mass, the atomic mass, and the atomic number. Now, once you have all these, you're able to make a Bohr-Rutherford diagram, which is basically just a simplified drawing of your element. So for fluorine, the first thing you would draw is a nucleus, so a circle to represent the nucleus in the middle. In the nucleus, you always put your protons you calculated, so 9p plus and 10 neutrons. And the nucleus is where all the mass is, and it should add up to 19, which it does there. And you start placing your electrons. You have 9 electrons to place. The general rule is that your electrons go on what's called a shell. So the middle is the nucleus, the shell is where the electrons are found. You can also call them orbits or energy levels. So I'll make the first shell. The first shell can hold a maximum of 2. So I'll place 2 here. I'll place 1 over here, and usually I'll place the other one on the other side. over here. That's 2. Once I place those 2, I have 7 left to place. I don't have any more room on the first shell because you can only fit 2 on the first shell, 8 on the second, and 8 on the third. So I'll make another shell here. I place 2, I had 9, so I have 7 left to place. So I do 1 on top, 1 on the right, 1 on the bottom, 1 on the left. Then I start to pair. So that's 4, then 5, and then 6, and then 7. So now I've placed a total of 9 electrons on 2 shells. If I had more, I'd continue placing until I ran out of space, which is after 8. Now an important term I want to go over here is the last shell here. The last shell is called the valence shell. The valence shell has special electrons called valence electrons. I'll call them VE, valence electrons. Those are the electrons on the valence shell, which is the outermost shell, the shell on the outside. They're important because when elements connect or combine, those are the electrons that will be doing the work because they're on the outside. So they're more accessible, they're easier to use. So you can see that fluorine has 1, 2, 3, 4, 5, 6, 7 valence electrons. It has 9 total electrons, but the ones on the outer shell, there's only 7. So there's a little trick you can use to figure out the number of valence electrons without having to draw them every single time. And that trick is you look at the group number. So anything in group 1 has 1 valence electron. Group 2 has 2. You sort of skip these ones for now. They're called transition metals. They're a bit weird for now. And you go here. Group 13 has 3 valence electrons. 14 has 4. 15 has 5. 16 has 6. 17 has 7. As you can see, fluorine is in group 17, 7 valence electrons. Group 18 has 8 valence electrons, except for helium. Helium only has 2, but that's okay. The 2 that it has fills its first shell, because the first shell can only have 2. So even though it seems like helium is breaking a rule, it's not really, because it still has a full shell. These are noble gases in group 18, and the thing is they have a full shell. 8 valence electrons, 8 valence electrons, 8 valence electrons, 2 valence electrons, but this is still full because it's the first shell. Just keep that in mind. It's not a trick, it's just you have to remember that because there's only 2 electrons there. How could it have 8 in its valence shell if there's only 2 electrons total in helium to begin with? So that's one trick you can use to find the number of valence electrons. So for example, carbon, it's in group 14, would have 4 valence electrons. Oxygen is in group 16, would have 6 valence electrons. Magnesium is in group 2, would have 2 valence electrons. You'll also notice if you go back to fluorine, it has 2 shells. The shells correspond to the period. So fluorine is in period 2. This is period 1 over here. This is period 2. So it has 2 shells. Something like sodium being in period 3, I could tell you right away that sodium would have 3 shells. You could draw it to try it out and see. Sodium would also have 1 valence electron because it's in group 1. 3 shells because it's in period 3. 1 valence electron because it's in group 1. And so that's a quick crash course on finding the protons, electrons, neutrons, drawing boards for diagrams, and some periodic trends, so meaning patterns or trends in the periodic table, like number of valence electrons and number of shells. Every element you can solve the same way. You just have to look at the numbers that they have in the periodic table.